Hello, young scientist. My name is Ayush P. Gupta, and in this video, we'll be seeing the theorems on moment of inertia. Okay, so these are the two theorems that are given on the moment of inertia. First is the parallel axis theorem, and second is the perpendicular axis theorem. Okay, so let us see what is parallel axis theorem. Okay, so parallel axis theorem says that a body is given to you. Okay, with the center of mass this point. Okay, and an axis a dash is passing through the center of mass. Okay, now so the moment of inertia of the body about this a dash axis, it will be equal to I a dash. Okay, and which is also equals to I com. Okay, that is the moment of inertia about center of mass. Okay, about an axis passing through the center of mass. Okay, now if I ask you what is the moment of inertia of the body about bb dash axis. Okay, so this is the bb dash is a axis which is parallel to the a dash. Okay, so this is the important this is important thing to remember, that is these two axes must be parallel. Okay, in the parallel axis theorem. So what is the moment of inertia about BB dash axis? So let's say the perpendicular distance between these two axes is your h. Okay, always remember this thing, that the distance between the two axes is taken as perpendicular distance. Okay, that is small h. Now if we see over here, then you can see this is the current scenario. Okay, and let's say we take a elemental particle again dm. Okay, which is at an r distance from the center of mass, or the uh, r distance from the axis of rotation a dash. Okay, so you know that the moment of inertia of this elemental particle dm about a dash axis will be given by diaa is equals to r square dm. Okay, similarly, the moment of inertia of this elemental particle about this BB dash axis will be given by the total distance from the BB dash axis, that is h plus r, that is h plus r whole square into dm. Okay, now dibb will be then equal to, you just expand it and you write it something like this, put on the integration so as to get the moment of inertia of the full body about BB dash axis. Okay, so you can see that upon integration you will get something like this. Okay, this is the first of all the moment of inertia about the of the body about a dash axis. Okay, this you can clearly see. Now this last term, that is the integration of 2hr dm, will be equal to 0. Okay, why equal to 0? So let's see this. So this term we have said is equal to 0, and this is because if you see that from the center of mass formula, if you remember in the center of mass chapter, rcom, that is the distance of the center of mass, is equals to integration of rdm upon integral of dm. Okay, so if you just take out this term on the left side and multiply these two terms, then you can see that you will get it something like this. Okay, now because we have already taken this origin as the center of mass. Okay, so you can see that rcom will be equal to 0. Okay, or you can see that the integration, the sum of moments of the of this whole all particles of this body is equals to 0. Okay, so this is the sum of all the moments. Okay, that is r into m. So because this is 0, so this term is 0, and if this term is 0, then you can see that from here, because h and 2 are constant, so again this only thing left in the integration is this. Okay, and this will be equal to 0. Okay, so you are only left with these two equations. Okay, sorry, these two terms. So hence you can see that ibb is equals to h square m. Okay, so h square m is your moment of uh, this m into h square is your separate term, and if you see this, that is iaa, which is the moment of inertia of the body about the a dash axis. Okay, so ibb dash x, so the final formula that we have got is the moment of inertia about an axis which is at an h distance from the center of mass of, or the a dash axis, is ibb equals to icom plus mh square. Okay, this m is the mass of the body, h is the distance between the two axes. Okay, remember this thing, that this is the perpendicular distance between the two axes. Okay, and this is the moment of inertia about the center of mass. Okay, so this is a generalized theorem, remember this result. Okay, and also to remember how we have calculated the, how we have got this equation also. Okay, so just remember this. Now let's see the application. Okay, so we already know that the moment of inertia of a rod of mass m and length l about an axis which is passing through its center. Okay, and perpendicular to it is given by I equals to 1 upon 12 ml square. Okay, so if you just see this and if we say what is the moment of inertia about the this rod about one of its end. Okay, you already know that it's 1 by 3 ml square. So let's see how we will be getting this by the parallel axis theorem. Okay, so we know that the moment of inertia about this axis, okay, that is one of the axis passing through the end, is given by using the parallel axis theorem, will be equal to ICOM plus m into distance between the two axes square. Okay, so this I is equals to then ICOM plus m, this distance is L by 2 perpendicular distance, so this will become L square by 4. So if you just see and apply this, you can easily get the moment of inertia of this rod of mass length about an axis through its one of its end as 1 by 3 ml square by 3. Okay, so I hope that you have understood the parallel axis theorem. Okay, so this is quite easy. Okay, just remember this formula. The second example is of the uniform solid sphere. Okay, so if do you know that the moment of inertia about the center of mass is 2 by 5 mr square, and what if I ask what is the moment of inertia of this sphere, solid sphere, about an axis which is passing, which is at a distance of capital R from the center of mass, or this axis, center of mass axis. Okay, so you will again apply this equation, you will get ICOM plus mr square. Okay, this distance is r, so I have already written as r. So if you just add up it, you can see that is the moment of inertia as 7 by 5 mr square. Okay, and note that this moment of inertia has increased. Okay, because the center of mass inertia moment of inertia was 2 by 5 mr square, but about this axis it is 7 by 5 mr square. Okay, so if you just see the moment of inertia, this is another example, that is moment of inertia of the uniform rod. Okay, so if this the same condition, that is the moment of inertia of the rod about an axis passing through its center is 1 by 12 ml square. Okay, now this two can be broken up into these two parts, that is half of the length on the left side and half on the length on the right side. Okay, so combining these two will be giving you the moment of inertia of this full rod. Okay, so let's see how we can apply this. So the moment of inertia, if you of this left hand part, you can see that we have got from this, that is 1 by 3 ml square, is your 1 by 3 into m by 2 into L square by 4. Okay, that you already know. If you just sum it up, you will get again the moment of inertia of the rod about the center of axis. Okay, so this was not the direct application but indirect application of the moment of inertia to this parallel axis theorem to find the moment of inertia of the uniform rod. Okay, so let's deal with the second theorem, that is the theorem of perpendicular axis. Okay, so the key points to note here, that is the this is valid only for 2D or laminar bodies. Okay, not for three-dimensional bodies. Okay, that is, it is valid for disc or some lamina. Okay, what is a lamina? Lamina is a body, you can say, which has the x in, which is in the xy plane and very has very small width in the z direction. Okay, so this is valid only for 2D bodies, remember this thing. Now let's say we take a lamina. Okay, and these are the two axes on which it lies, that is x and y axis, and z is the axis which is perpendicular to this lamina. Okay, and lamina is a rigid body again, and this point, that is this point where the all the three axes meet, that is the origin, may not be the center of mass of the body. Okay, so remember this thing. So what does the theorem of perpendicular axis says? That it says that this moment of inertia about the z axis is equals to the sum of the moment of inertia of the two axes which are perpendicular to it and are also perpendicular to each other. Okay, so that is, you can see that Iz is equals to Ix plus Iy. Okay, and the condition is Z is perpendicular to both of them. Okay, you can see Z is perpendicular to Y, Z is perpendicular to X, and also X is perpendicular to Y. Okay, or Y is perpendicular to X. So when these conditions are met, then you can directly apply Iz equals to Ix plus Iy. Okay, remember that moment of inertia is a scalar quantity, so there are no vectors over there. Okay, so or you can indirectly say that all three axes, that is Z, X and Y, are all mutually perpendicular to each other. Okay, so let's see the proof of this theorem. So again we have the same, the origin, let's say we have a point P which is have has a coordinate x y z. Okay, now sorry, this P actually lies in the plane of the x and y, so this P has a coordinate of x y comma 0. Okay, so x y and z axes are perpendicular to each other from the are mutually perpendicular. Okay, and x y are the distances to the point P from the respective axis, that you know that. Okay, that's simply the coordinate definition. So the moment of inertia of this point P about this x-axis will be equals to your m dm into your y square. Okay, so the sum of all these such points on the body will be the summation of mi into yi square. Okay, why you have taken y in the case of x? Because the distance of the point P from the x-axis is your y. Okay, not x, remember this thing. And for the y it is simply equals to your x. Okay, that is this distance. So if you see, and for the, if you see what is the moment of inertia about the z axis, then you can see that the moment of inertia about the z axis will be equals to your distance from the z axis. Okay, that is the r. You know that the distance of point P from the origin is your small r. Okay, that is this distance. So the moment of inertia will be equal to summation of the moment of inertia about the z axis of all the points. Okay, so these are the three equations that you have got. Now you know that r I square, that is this r I square equals to x I square plus y I square. Okay, why I have wrote I is for the individual particles. Okay, so I can number from 1 to infinity. Okay, so for a point this equation is valid. Okay, that is, you can see r square equals to x square plus y square. Okay, now just combine these three equations, so you get Iz. If you see this equation Iz, so Iz will be equals to this, and if you put this xi square plus yi square in the ri square, you will get something like this. Okay, open up, multiply it, you will finally get Iz equals to Ix plus Iy. Okay, so try to understand how I have derived the proof. Okay, the proof understanding is must. Even though you don't remember how to these all these calculations, just remember the method. Okay, how we have proved. Okay, so they remember this result, and now let's see the application of this result. Okay, now you know that for a disk of mass m and radius capital R, the moment of inertia about a dash axis is equals to half mr square, that you already know. Okay, now again if you are confused, this is the moment of inertia about the axis perpendicular to the disk. Okay, not this o dash axis but the a dash axis. Okay, so if I ask you what is the moment of inertia about the o dash axis of this disk, now there are two approaches. Either you can take the elemental mass approach, which is little calculative in the, okay, or tricky, or you can just use this perpendicular axis theorem. Okay, so this is your figure, and we have to calculate the moment of inertia about the o dash axis. Okay, so with the perpendicular axis method, first of all verify that all the three axes are in the perpendicular to each other. Okay, that is mutually perpendicular. This is the condition for this theorem. So this is x-axis, this is y-axis, this is z-axis, and we have to find out the moment of inertia about the z and z-axis. Okay, so apply Iz equals to Ix plus Iy. Okay, and you already know that Iz equals to half mr square from here. Okay, So also you can see that ix is equals to y iy, okay, which is due to the symmetry, because the disk is symmetric. So whether you calculate from y axis or x axis, it is same, or any axis which is which is passing as a diameter to the disk, okay, is same. So 2ix is equals to iz, and ix is equals to 1 by 4 mr square, okay. That is the moment of inertia of the disk about an axis which is passing to it as diameter, okay, or in the plane from the center, is equals to your 1 by 4 mr square, okay. And you can see that this moment of inertia has decreased, okay. Moment of inertia about the z axis was greater, that is half, and now it is less, that is 1 by 4, that is 0.25, okay. Here it was zero point 0.5, so remember this thing. So this again the conclusion, okay. So note the axis carefully. From the moment of inertia about this axis is half mr square, and about this axis is your 1 by 4 mr square, okay. Now the another term that comes frequently in the moment of inertia is your radius of gyration, okay, or which is represented by k. Now what is k? That is very very simple, okay. Moment of inertia about the disk, you know, that is half mr square, okay. Now for k you just have to put I is equals to mk square, okay. That is k is the effective distance of whole mass from the axis, okay, or mass is assumed to be concentrated at that point, okay. That is, if you just calculate k from this formula and put I as half mr square, you will get k as r by root 2. So that this is the distance from which the whole mass is accumulated, okay, or concentrated at that point. So k for, that is the radius of gyration for a disk, is your r by root 2, okay. So you just have to do this thing, that you put the moment of inertia after calculation as mk square, okay, and compare it. If you just compare it, you can get the k as r by root 2 over here, okay. So the physical significance of radius of gyration is again the effective distance of whole mass, okay. That is, you can replace the full body with the point mass, okay. So and that point mass will be m, and at a distance of r by root 2 from the axis of rotation, okay. So just replacing the whole body with the simple particle, okay. So I guess this is all for the video, and you have now understood that two theorems on the moment of inertia, okay. If you haven't understood, then again and again repeat this thing and try to learn how we have derived the theorems, okay. So good luck.